equals the rate of the reverse process. Remember, conditions such as temperature, pressure, and concentration must remain constant. On a microscopic view, there is constant change. But on a macroscopic view, it seems as there is no change taking place. Now, let's see how the characteristics of a dynamic equilibrium can be applied to chemical reactions. Some chemical reactions are reversible. For example, when ammonia gas and hydrogen chloride gas react, they form a white cloud of tiny crystals of ammonium chloride at room temperature. And when ammonium chloride is heated, it forms ammonia gas and hydrogen chloride gas. The gases react with each other to reform a white cloud of ammonium chloride. Although these reactions are reversible reactions, this is not an example of a dynamic equilibrium yet. Can you suggest why? For a dynamic equilibrium, we need a closed container, and the forward and reverse reactions must take place under the same conditions at the same time. The rate of the forward reaction must also equal the rate of the reverse reaction. Right, so let's heat some ammonium chloride in a closed container. After a short while, all we can see is that the container is filled with white fumes. There doesn't seem to be any changes taking place. But what's happening at a microscopic level? The ammonium chloride solid decomposes to form ammonia molecules and hydrogen chloride molecules. This is the forward reaction. Notice that at the same time, some hydrogen chloride molecules and ammonia molecules collide to form ammonium chloride as a product. This is the reverse reaction. Also notice that the total number of ammonia molecules and hydrogen chloride molecules remains the same. So the rate of the forward reaction must be equal to the rate of the reverse reaction. We call the dynamic equilibrium established in the closed system a chemical equilibrium. Can you suggest how we can represent the chemical equilibrium in the container? For phase equilibrium, we combined the equations for the forward and reverse reactions. Let's do the same here. The forward reaction shows the decomposition of the ammonium chloride to form gases, and the reverse reaction shows how the gas combined to form the solid. Next, we turn the reverse reaction around, and then we can add the two reactions together. The double arrow shows that the reaction is in a chemical equilibrium. In this chemical equilibrium, the reactant is a solid, but the products are both gases. We call this a heterogeneous chemical equilibrium. Many learners find it hard to understand what it means to have the rate of the forward reaction equal to the rate of the reverse reaction. Let's think of the forward reaction as a man throwing apples over his neighbor's wall. At first, only man A throws apples because man B does not have apples to throw. Eventually, man B starts to throw apples back. Think of man B throwing apples back as the reverse reaction. At first, man B is slow at throwing back, but he eventually speeds up. Man A and man B end up throwing apples at the same rate. Can you see that the number of apples on man A's side stays the same, and the number of apples on man B's side stays the same? We say they are in dynamic equilibrium. Chemists like to represent chemical equilibrium using two different graphs. The first graph is the rate of reaction against time, and the second is the concentration of reactants and products against time. Before we draw the graph together, let's take a look at the microscopic view of a reaction. In this closed container, we have molecules of A2 and molecules of B2 at the start of the reaction. The molecules gain energy and begin to move around faster and collide with each other. Some of these collisions are effective, and new molecules AB form. At first, there are many effective collisions, and the number of AB molecules increases quickly. But then, molecules of AB start colliding with each other to reform molecules of A2 and B2. The forward and reverse reactions continue to take place at the same time until the number of reactant molecules and product molecules stays constant and the rates of the reactions are equal. Right. With that microscopic view in mind, let's work out what the graph of reaction rate versus time will look like. We'll show the rate of forward reaction in red and the rate of the reverse reaction in blue. When the reaction starts, the forward reaction has a high reaction rate. There are many effective collisions and lots of product molecules form. But as the reactants form products, the rate slows down. At the same time, the reverse reaction starts from no reaction rate and increases. When the rate of the forward reaction and the rate of the reverse reaction are equal, chemical equilibrium is established. It's not easy to see when reaction rates are equal. It helps if we measure the number of product or reactant molecules present in a closed system. That's why the second type of graph is important. To draw this graph, we will consider the reaction of nitrogen gas and hydrogen gas to form ammonia gas in a chemical equilibrium. This reaction is important in the fertilizer industry. The reactants and products are all in the same phase in this chemical equilibrium, so we call it a homogeneous chemical equilibrium. Let's have a look at the microscopic view of this reaction as we look at the graph. At the start of the reaction, we have a high concentration of hydrogen molecules and a lower concentration of nitrogen molecules, indicated by the green line. There are no ammonia molecules at the start. When the forward reaction begins, the number of hydrogen molecules is used up quickly and the concentration decreases sharply. The concentration of nitrogen decreases too, but not as quickly. The concentration of ammonia, the product, increases steadily from zero. The reactants are not all used up because the ammonia molecules break apart to form hydrogen and nitrogen. Now, let's look at the point where the reactions reach chemical equilibrium. Notice all the graphs become less steep and slowly become parallel horizontal lines. At this point, the concentration of the reactants and products is no longer changing. Chemical equilibrium is established. It's important to note that the number of molecules does not need to be equal for chemical equilibrium to be established, but the total number of molecules remains constant. I hope you find these graphs useful in describing and representing and interpreting what happens in a chemical equilibrium. Here's today's task. In a closed 1 decimeter cubed container, 5 moles of hydrogen react with 4 moles of iodine to produce hydrogen iodide. At chemical equilibrium, there are 4 moles of hydrogen iodide present in the container. 1. Sketch a graph of reaction rate against time to show chemical equilibrium. 2. Sketch a graph of concentration of the reactants and products showing when chemical equilibrium is established. For more information, please visit our website on www.mindset.co.za/learn.